Last time we collected some data, which I'm just going to do a nicer version of the table of here, which was from the people that were present, the number of siblings. And then we did the frequency. And if you're an only child, at least the way we decided to count them, there was 2 of you. And 2 in the family, there was 10 of those. And 3 in the family, there was 3 of those. 4 in the family, we had 1. 5, 6, 7, and 8, and 9, I believe. No, I missed that. 1 with 7. I'm not sure how neat that is, but at least it's different, right? And we call these, this particular table, we call this a frequency table. It's like just an introduction to how you could summarize a whole load of information, numbers in this case, in a way that makes it a little bit easier to see what's going on. And if your data is in the form of a frequency table, then you can normally, just from this table, you can normally answer quite a few questions. You could, for instance, notice that, wouldn't you agree that having 2 siblings in total was the most common answer that you're likely to get? I'd be pretty sure that if we chose just a general person at random in America, that maybe 2, probably 3 would be the same sort of an answer. So that does kind of match quite well. There is a kind of pattern, doesn't it? Start off relatively low, then it builds up really quickly, and then it drifts away to 0. And so we have a kind of pattern in the data. It's not like jumping around big, small, nothing, small, small, smaller, big. It's not jumping around. It has a kind of clear-cut pattern. And so that is what we call a relative frequency. Now, if I wanted to create from this table, from this table, if I wanted to create a picture version of that same information, it might go something like this. Along the bottom, I would say number of siblings, which is typical. And then the vertical one would be the frequency. And since the biggest number I need is 10, I can go 2, 4, 6, 8, 10. So I use some kind of scale that fits the space that I have got. And then I would simply probably do something like this. 1 child in the family, there was 2, so I do a rectangle. And then right next door to it, you'd get 10. And then right next door to that, 3, you would do 3, which is about this amount. Right next door to that's 4, which is 1, which is this amount. And then really nothing for 5, nothing for 6, 7. Should have planned ahead here. In 7, got 1. There's 8. Oops. There's 8. Don't know why I'm changing my color scheme here. There's 8. There's 9. And right at the end, there's a 10. I'm sure that you've probably seen these types of pictures before. We typically call these histograms. Would it be fair to say that for most of you, this is not new stuff? You've seen histograms in other classes, right? Whatever it might have came from, geography class, whatever, there might have been a histogram, social science class, something like that. So what we're going to introduce you to is different kinds of tables and graphs that can be used with those tables. Tables are very good for getting numbers and details, but I think graphs are much easier to see patterns. When I look at this, the pattern that I see, and I think of it as like hills. Can you see it's basically got one little hill and it goes like that? That's its basic shape. And we look at histograms and their shapes, and we try and describe those with various words. And when you're using a table, it's very useful for getting exact numbers. It's a little bit harder, especially when the table is quite large, to see big picture things. Now, next kind of frequency table is called a grouped frequency table. And in fact, this is the version that the textbook focuses on. So I want you to imagine that we collected data on the ages of people. So you get whatever it is, a group of 50 people, and you say, what is your age? And they tell you, right? So to save things, I'm just going to make up some data. So I went to a shop and I found out what the ages of every person who was in the shop when I arrived. And I'll do them in order. So there was a 9-year-old, there was another 9-year-old, there was a 10, there was another 10, there was a 12, there was a 15, there was a 17, 1, 2, 3, 4, 5, 6, 7, I'm not right here, 8, 9, 10, right, I'm trying to do a row of 10. And then it went up to 20, 23, 23, 23, 24, 25, 27, 29, 29, 30, 31, 33, 35, 39, 41, 47, 52, 56, 61, and then 71. So 30 people, and this is their age group. It wouldn't be a good idea to use this kind of single frequency table to summarize that. Can you imagine the main problem? Wouldn't this table be huge? I mean, it'd be really long. Wouldn't there be a lot of zeros in it, right? There's nobody who's 26 years old, right? There's nobody who's 62 all the way up to 70. And if you do these tables, you are not allowed to miss out zeros. You have to put a number in even if nobody has that value. So in a lot of data, because the data varies so much, right, from the smallest to the biggest, in such cases, then we do what's called a grouped frequency table. And to kind of do that, what you do is you set up your first column is going to be your age. And your second column is going to be your frequency. Now, I have a lot of choices of how I could split this up. This is how I am going to split it up. I'm going to do a newborn baby who isn't even a year old up to 9. It's going to be my first group. Then my next group is going to be the 10 to 19-year-olds. Then my next group is going to be 20 to 29. My next group is going to be called 30 to 39. My next group is going to be called 40 to 49. Just keep going till I finish here. Then I'm going to go 50 to 59. I'm almost done. 60 to 69. And 70 to 79. Now, a couple of things about these groups. One of the most important things about these groups are, to be fair, aren't they all the same size? Right, I don't do 0 to 20-year-olds and 21 to 25-year-olds, right? You make them all the same size. That is a kind of standard thing that we expect you to do, right? Same size groups. Now, for each of these groups, all I really need to do now is count who is in that group. So are you a baby that's just born to 9 years old? So 1, 2, 3, 4, 5 belong in that group. There you go. Now the 10 to 19s are in this group here, right? And that also happens to be 5. The 20 to 29 group is everybody in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 of those. The 30s are this one here, all the way to there. 1, 2, 3, 4, 5. I don't know why I keep picking 5s. The 40s are 1, 2. The 50s, 1, 2. The 60s, they're just one of those, and one person in the 70s. Are you comfortable about the way in which this was created? You have some groups, and then anybody in that group, you add them up, and you now make this kind of diagram. It's called a grouped frequency table. Okay. Now, let's introduce you to some names. I'll take one of the groups at random. There's no particular reason why I chose this group. But suppose you look at the 20 to 29. That's a group, right? It's also called a very strange name. It's also called a bin. I think it comes from the idea, can you imagine that you had bins or little buckets and you had cards with the age, and when you got that age, you threw it into this bin, right? You threw it into that bin. And so these are collections, right? Collection bins for things. So that might be where this weird name bin came from. And we give the smaller of the two, that's this fella here, is called the lower class limit. And this fella up here is called the higher class limit. So if I was talking about the third group or the third bin, the lower class limit is 20 and the upper class limit is 29. If I was talking about this group or bin, the lower class limit is 60 and the upper class limit is 69. So we're just introducing vocabulary. So if you see a question and they say lower class limit or upper class limit, do you now know what they're talking about? You can understand from the term. Are we good? Now, a new guy, choosing your color. And this thing is called the bin size. The bin size is essentially how many different numbers are in the group. Okay, in the group or the bin. Well, let's take this guy. There's 20 to 29. Do you know it's a common mistake? People say there's 9 numbers in that. There isn't. How many numbers actually fit inside that bin? How many different numbers could you get in that bin?
10.
10. So that is just a simple thing. And I know I probably do it myself when I'm careless. Isn't the temptation just to say 9, right? If you do that calculation, will you please remember to add an extra 1? And that's because you're counting the first number and the last. And when you do a subtraction, it doesn't quite do that for you, right? So if you can imagine, I'm making a weird interval. Can you imagine an interval that was 18 to 26, right? So that was a group, 18 to 26. And I asked you, what was the bin size? I think 26 take away 18 is a good way to start, right? But when you subtract this from this, don't you get the answer 8? But what do you just remember to do is add that extra 1, and add 1 for luck, or whatever you want to phrase it to yourself, right? Add 1 for luck, and now you know what we call the bin size. So in this particular case, the bin size is 10, right? So far, so good. Now, I created these particular bins, these particular groups, because to me, these seem quite natural numbers, don't they? They're kind of easy to, your brain reacts to groups that look like this quite well, right? But let's just imagine that I had a different story. It's not ages here, it's just some numbers, right? And the smallest number I have is 3, right? So that's the smallest. And then it goes all the way up to, and the biggest number is 125. And I would like to know what size bin, right? So here's the question. What size of bin you would need to only have 1, 2, 3, 4, ooh, I don't know, to only have 7 groups. So I want to make a table like this, but I only want it to have 7 rows. But I don't want 27 rows, I don't want 40 rows, I don't want 2 rows. I want 7. So how do we calculate the bin size? So this is what you do. To get the bin size, you take the largest number and you subtract the smallest. And then you divide it by how many you want. So if you want 7 groups, you divide it by 7, right? If you want 10 groups, you divide it by 10. Now the largest number I have here is 125. The smallest number I have 3, and then you divide it by 7. When I look at my calculator here, 125, take away 3, divide that by 7, I'm going to get this rather ugly number called 17.43 and some stuff. We are not going to start the group with 3 and then have the next number 20.43. That would be really silly. Bin sizes have to be whole numbers just to be practical. So what you do in this case is you could pick 18 and that could be your bin size. And 18 would work. You could pick 15 or you could pick 20. Now they're not 18, that's a little bit smaller than 18, this is a little bit bigger than 18. But the reason I'm saying these are also choices is for cosmetic reasons. Would you agree that if you went up in 20s, it would be nice looking groups? The groups wouldn't start and finish at weird numbers, hopefully, right? But since we can only choose one, typically you just round the thing off and choose that one. So I'm going to choose 18. So my first group would look something like this, 3 to something. Now remember, I want 18 numbers in this group. Your fingers can actually help, because if you add 18 to this guy, right, you'd get 21, agreed? 18 added onto 3 would be 21. But let's count how many numbers that is. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Uh-oh. We'll try again. 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh. Do you know there's 19 numbers in that group? I had to do a double take because I think I miscounted. But don't we want 18? So to get 18 numbers, do you see your first group has to be 3 to 20? It's kind of fiddly, this, isn't it? You have to keep, that's why I use my fingers a lot, because it's hard to tell. Let's do a double check. If you subtract them, isn't it 17? And how many numbers do you get when you subtract 17? Don't you get 18 numbers in the group? Does that kind of convince you that's the first group? Right. Now, once you've got the first one, don't you start at 21 and then you finish at some other number? What would be the number to finish with this second time then? Well, couldn't I just add 17, which is a short way of doing it, right? And that would get me 38. Then I could start at 39. And if did I say add 18? Add 17, good. Add 17, that's 18. Oh, 18 going this way, that works better. 6, 56. I'm running short of room here. Here are the first three groups. If you look at the difference between these, it's 17. But if you look at the difference between the two end numbers, do you see it's 18? So the trick to doing this is be very careful about your first group, right? Make sure you get the right start and finish number. And if you're going to do an interval, right, a bin of 18, all you need to do is 18, 18, 18, 18, and 18, 18, 18, 18, and the rest of the groups will be fine. And you don't need to keep counting on your fingers every single time how you're doing it. So make sure you're careful with the first one. And then if the interval or the bin size is 18, add 18 to that guy, then add 18 to him and keep going. And when you get to the last group, you'll know that you're in the last one because won't it have 125 in it? It won't necessarily start with 125. It won't even necessarily finish with 125. But somewhere in that interval, you should find that there's 125. Are we comfortable with that kind of process? Right. Now, just for argument's sake, suppose it was the same data, but I didn't want 7 groups. I only wanted 5 groups. So I'm just going to go through the same basic process and we'll start with a few of the intervals and see what we get. So to get the bin size, you take the largest, subtract the smallest, and divide it by how many groups or bins that you want. That's 122 divided by 5. And I get about 24.4. I think I'm going to go for 24. If I round it off, maybe 25. Any suggestions for which one you think might be a good one? Because there's a little wiggle room going on here. I could 25. Do, yeah. Would you agree 25 is just easier in the head? Right. So in this case, I'm going to start with 3. Right. So my first group starts with 3. Okay. We got to figure out who this second guy is. 25 numbers, right? Will this second number be 28 or will it be 27?
7.
Yeah.
Yeah, the first one would be 25.
The first one's a fiddly one, right? Yeah. But once you've got them, can't you just say add 25, add 25? Oh, that's 5, 2. Yeah. Add 25, add 25, add 25, add 25, add 25, add 25. And one more for luck. Add 25. So you can see how you would create your groups, and then you would just add up what you did.
I have a shortcut. I don't know if it would be a good
Oh,
one.
go for it. I like shortcuts.
So when we're trying to figure out the groups, and we know that we have to separate it by 25, can we just add 25 and start the next column, and then -1 to get what we need? No, for the first column. So you minus.
Oh yeah, add 25 and take away 1. Totally agree. Yes. So see, you get the second number, the 27. He's saying, if you're going to use a 25, right? He's saying, I just add 25 and then remember to take away 1. And once you've got this one, aren't the others pretty easy? Yeah, that makes sense to me. That works. Are we cool?
Yep.
Right. So, groups frequencies. Now, if you want to do, you would certainly expect to do. You're going to eventually do histograms of these data, right? But that does involve a little bit of a problem, because do you notice that this thing finishes at 9 and this one finishes at 10? Not all the numbers that you're going to deal with are whole numbers. Can you imagine that sometimes you're going to get numbers that are 9.2 or 9.9? Can you imagine the data might have some decimals in it as well as whole numbers? You still want to use these groups, but how do you get around that problem? Well, what you do is you just pretend that the data has been rounded off. So if you have a number and it's 9.2, won't you just count it as a 9 and it belongs in the first group? But if it's 9.8, won't you use it in the second group? Because isn't 9.8 to the nearest whole number is closer to 10? So that's how you're going to deal with that. What do you do if your data isn't always whole numbers, right? If some of your data is decimals, you basically treat all your data as if it was rounded off. Now, I'm going to draw some histograms here, only so that we can get used to how we describe shapes of histograms. So it's really getting you used to the naming process. Imagine I have a histogram. We won't bother about details, but these are what the rectangles look like. I don't know why, but for me, it kind of helps to draw a kind of line through it, you know, just to get a picture of it. This shape has a number of features that we have names for. The first name is called unimodal. If you have a rectangle, a histogram like this, and there's only one hill, we say it is unimodal. Can you imagine that you might get data that's really got two hills? The hills don't need to be the same size, but would you agree that there is a kind of one hill here and then it picks up again and it goes down again, right? When it's got this, we call it bimodal. That means it has two hills. So if you ever get a question that says, describe the histogram, one of the things you may be choosing is that it's unimodal in shape or it's bimodal in shape. Uni and bi come from, I think it's the Latin, but if it's not, it's definitely the Greek. I seem to remember unicycle and bicycle. Doesn't unicycle have one wheel and bicycle is two? So it's from the same root. Unimodal, one hill, bimodal, it's got two hills. You might say, well, what happens if it's got 3, 4, and 42 hills? I mean, do we just keep naming them? You know, like, I don't know, trimodal or something, and quad modal? Nah, we don't. We just say it's multimodal. I don't even think they've got a multimodal, so I wouldn't worry too much about that term. But unimodal and bimodal are very common. So that's one feature that a histogram can have. Unimodal, bimodal. This shape is unimodal. It goes up and then it tails off. Do you notice that it tails off to the right-hand side? Right. There's a lot more stuff happening on the right-hand side of the hill than there is on the left-hand side. You agree? When you see this specific shape, this shape here, we say that it's skewed to the right. So if someone was saying, describe this shape, one of the features that it has is it's skewed to the right. Now you notice it's this piece of the shape here that tells you. This piece of the shape here is called the tail. So if there's a big long tail to the right, it's skewed to the right.
Professor?
Yes.
My power just went out and I'm on a hotspot right now. But my phone's on 15%, so I probably have just a few minutes left of class unless
Right.
the power comes back on. I'm
Okay,
just letting you know.
Right. Well, I'll tell you what I'll do right now since you are here and it's not your fault. Will you all say hi right now to get your attendance, including him? So I'll give you a moment to just go to the chat and say hi. And that's how I check attendance. I just look at the comments and I look at it at 34 minutes up to 35 minutes. So if you said hi in that window of time, you were here. Last few seconds. Still going, so I'll wait until the last hi disappears. Looks like we're done. If this guy is skewed to the right, have you any guesses what my next picture is going to be called and what it might look like?
It's skewed to the left.
That's definitely what it's going to be called.
The tail's gonna be more on the left-hand side.
Yeah. So it's going to start. And it's going to die away quite quickly. And of course, just for completeness sake, this is the tail, right? Raina, since you've just arrived, will you say hi on the chat screen so I can tell that you've arrived? This is skewed to the left, this is skewed to the right. These shapes are very common. I'll give you some examples of where you might get shapes like this. Let's talk about scores in an exam, right? If this was the kind of shape I got from scores for an exam, wasn't it a really hard exam where a lot of people didn't do well, and then it was drifting away and only a few people did really good? Wouldn't this be an example of what a really difficult test's distribution of test scores would look like? On the other hand, wouldn't this be a very easy test? Because a lot of people got really good scores and there weren't that many who did poorly. Now, there is a third shape that we typically deal with. And we call this symmetric. Now, typically symmetric is unimodal, which it is, right? And it's roughly balanced on either side. Don't expect perfect matches, right? You are allowed a little bit of wiggle room to be symmetric, right? Because in real life, don't data have little hiccups, right? So although this one is skewed to the right, can you imagine maybe that little rectangle there was a little bit high and it looked like a little bump? It'd still be considered skewed to the right, right? One little hiccup doesn't really kill the basic shape. Can you imagine this one here had a little, that rectangle was maybe a little bit bigger than the one next to it? It still would be considered. So the same thing is true about symmetric. So if you create a histogram, one of these pictures, you should be able to tell if it's bimodal or unimodal. If it's unimodal, you should be able to say symmetric, skewed left or skewed right, just by looking. There's not much more to come in the naming. And then we get into kind of the weeds after that for a while. Now, this particular histogram doesn't have an awful lot of shape to it. It doesn't have a lot of structure. I guess if you looked really hard, you might see a little bit of a bimodal, but it's not much if it's got it. Would you agree it's definitely not skewed left, right, or symmetric, so we wouldn't use any of those terms. What is most interesting about this histogram is you see this little guy over here. It might even be two guys. Do you see this one here? Do you notice there's a huge gap and then there's him? When you see that happening in the histogram, this fella out here is called an outlier. And an outlier is any extreme value in your histogram. And this particular outlier isn't a very big number, so it's a big outlier. Can you imagine a different picture? I don't want to draw another picture, but can you imagine this data where the line went this way and there was a little guy sticking here on the left-hand side on his own? So he would be an outlier as well. He'd just be a very small outlier. Outliers are quite interesting because sometimes the outliers are more interesting than the boring data because everybody's kind of the same. If I did a histogram of the salaries of people who lived in Washington State, right? So imagine along here is how much money you have. And this might be what you would get. Most people, their salaries are over here. I think that's Bill Gates. And I don't know some other back, but there are probably a couple other billionaires in Washington State, and that's them. Do you see that the main data, right? The normal, typical person lives here, but the outliers live in a totally different world, right? There's technically there should be a nice, big, obvious gap, and then so in this case, don't all three of them count as outliers? You don't just need to have one outlier; you can have many. Now, if I did this to scale, in other words, this here is exaggerated to prove a point. Do you know if I did this to scale? That's what it would really look like. Because doesn't Bill Gates have billions? So if I'm going to have a billion here, won't we really not have an awful lot of room for this? So what we have noticed is that when you construct a histogram, if you try and include the outliers, don't you muck about with your picture to the point where you can't see anything, because they're all crunched over here because he's so big. So what you very often do, or they are so big, is that you take these guys and you remove them from your data set. You just don't use them. And then you make a histogram of like everybody that's left. And then you can see what the heck's going on for a typical person in Washington State. So when you've got your data and you think, oh God, I'm not going to use that 42 billion, that Bill Gates, if I try and use his number, I'm never going to get a decent picture, right? I won't be able to see anything because he's wasting the picture. Then you just take him out and you look at what's left. Any questions so far? I haven't shown you how to create one of these, so I guess that's what I should do now then, right? So it's a little bit more difficult than you think, or you would hope, and that's fine. The good news is once I show you one, you've seen them all, right? So let's suppose that I collect data on a test that a class got. And I'll have to start away over here. So we have 1 to 10 and 11 to 20 and 21 to 30. And just to keep my life simple, 31 to 40. So can you see in this particular very simplified version, and the reason I'm doing this is We could do this with 20 rows, but if I show you how it works with 4 rows, you can figure out what it's going to look like in bigger situations. So we've got some data. I'm just going to put some names. This number here, the small one, is the lower class limit. This guy here is the upper class limit. And then we have these guys. And we go 0.5 to 10.5. And then we go 10.5 to 20.5. And then we go 20.5 all the way up to 30.5. And the last one is 30.5 all the way up to 40 plus 0.5. And these are called class boundaries. These are actually the numbers that you use typically to create your histogram. So I'm going to go over, and I need to know the frequency. So I'm going to stick it over here. So let's suppose in this particular class, 6 people, 14 people, 5 people, 3 people, right? Then our histogram would look like this. Along the bottom, you'd put what the thing is, and it's the class test. And then vertically, you put the frequency. And since I know the biggest number is 14, I choose a scale, 2, 4, 6, 8, 10, 12, 14, 16, 18, and so on. Go like that. And then you do a scale, and you go 0.5, 10.5, 20.5. You can make that scale 2 boxes, whatever you feel comfortable with, right? And then 30.5, and finally 40.5. My first interval, which was numbers between 1 and 10, the class boundary aren't these the numbers that would round off to give you 1 to 10? Right? So 0.5, 6, 7, 8, and 9, wouldn't that round off to the 1? I wouldn't 10.1, 2, 3, 4, that would round off to the other one. So that would be the rounding off guy. So what that allows us to do is, for our first guy, it's going to be 6 high. The next interval, 10.5 to 20.5, is going to be 14. The next group is going to be 5. And the last group is going to be 3. So when you do your histogram, do you notice that you use these boundary points, these class boundaries, so that you can have a rectangle that doesn't have any gaps in it? You see, this one finishes at the place where this one starts. So that's a little bit awkward, but that's how they do it. There's not an awful lot I could ask you about this one, but I think there is one. Unimodal or bimodal? Let's get the obvious question out of the way. Agreed? First one?
Unimodal.
Yeah. And does this shape have any outliers? Nah. I don't think I could say this one is really skewed to the right. Would you agree it's not enough information really to get that? No. But can we pretend there was 3 or 4 more rectangles over here? If there were 3 or more rectangles, wouldn't I then probably say skewed to the right? But right now, I think I'd be pushing it to say skewed to the left. So histograms don't need to have any structure. Some of them just are New York skylines, right? They just got them down like a yo-yo. Nobody can tell because there's nothing there, right? But if they do have a structure, you've got it. So from the lower and the upper, you then create these guys called the cross boundaries. These allow you to create the histogram, right? So far, so good. There's another heading that some of the homework questions want you to do. That's why I've left some spaces here. Midpoint. In this interval and in this class boundary, there's a number in the middle called the midpoint, right? Can anybody remember how you get the midpoint? If I know the start with a 1 and I finish with a 10, how do you get the midpoint?
Divide by 2.
Yeah, add them and divide by 2. So different color. 5.5, 15.5, 25.5, 35.5. There is a common theme to every single thing that's happening in this table. Do you notice that once you got the first number, is everybody 10 more than it? Once you've got the second number, everybody's 10 more than it. Have you noticed that this number, everybody's 10 more? Have you noticed that the midpoint, everybody's 10 more? If you wanted to complete this table, wouldn't you really just need to work on getting the first row right? And as long as you know that 10 is the magic number, and by the way, 10 is your bin size. So once you know what the bin size is, can't you create the rest of the numbers? So it's not like you have to keep doing all sorts of the same calculation over and over again. You only really need to do it once. And I went and moved my frequency probably more than I should have. So can you imagine I picked that up and stuck it there? Because there's a funny gap that shouldn't be there. And you might say, well, that's cool. Is there anything else that could be added to this table? Well, there are. I'm just going to have to go this way. Although you don't get an awful lot of questions in these particular section of homework, some of them are quite long, as this one is. So I've got upper and lower limit, class limits, I've got class boundaries, I've got midpoint, I've got frequencies, 2 more columns. This guy is called a relative frequency. These are frequency. That means 6 people got somewhere between 1 and 10 in the test. 5 people got 21 to 30 in the test, right? That's frequency. How many people or numbers belong in each of the groups, right? That's what a frequency is. A relative frequency is what fraction of the total is that. We don't typically write the answer as a fraction because fractions are ugly. We tend to take that fraction and convert them into decimals or percentages because they're easier for the brain. So I guess it should have been called decimal frequency or decimal relative frequency or something. So let's show you how it works. There is a total number of people in this class. It was 28 people. The first one is 6. So 6 out of 28 people. That would be the relative frequency if you wrote it as a fraction. I guess I could simplify that fraction, but I'm not going to. In general, you just convert it into a decimal, in which case, would you agree that I don't write lots of decimals? That would be impractical. So how about we'll have a rule unless the questions in the web assigned says differently. How about 2 decimal places? Is that a good rule? That'll do. So 0.21 goes there. Right, the next one is 14. So 14 out of 28. Oh, doesn't that mean half the class got somewhere in that group? Right, 0.5 of them, half the class. And the next one is 5 out of 28. That's, to me, rounds off as 0.18. And the last one is 3 divided by 28. And I make that about 0.11. Agreed? Now, sometimes the relative frequency is a decimal, and sometimes it's a percent. It really just depends on what they ask you for, right? If they just say relative frequency and they don't mention anything else, go with the assumption that they want the decimal. If they mention percentage in part of the, I want the percentage relative frequency, something like that, then go for the percentage, right? So if they don't mention anything, we'll assume it's decimals they want, and otherwise it's percentages. Are we cool with that? And this table has got everything you could ever want to know about this data. And so we're putting in lots and lots of stuff. There is a little check I should do. I'm going to add all these decimals up. And if I add them all up, that's 0, 1, 2, 3, 4, 5, that's 0. And I get 1.00. Why is that a really good answer? Why am I happy that it added up to 1?
Because it counts for the whole percentage as in the whole of the equation, so the whole set of data.
Right. So if I did the percentages, shouldn't I get, I hope, 100%? Now, there is a kind of caveat to that. Do you know I've rounded off to 2 decimal places? Can you imagine sometimes that might introduce a little bit of error? It doesn't mean you've done anything wrong, but can you imagine it might only add up to 0.99, or it might add up to 1.02. That's totally okay. That just happens, right? If I rounded off to 4 decimal places, I might do better, right? If I round off to 2, it's more likely to happen. And the same thing will happen with the percentage. If you get 99.8%, you're probably safe, right? It means you did it right. The difference is caused by rounding off errors. On the other hand, if you add it up and it's 1.72, you're wrong, right? Something's not right. You can't get a totally 1.72, right? It should be almost 1, almost bang on. If you got 102%, that's okay. But if you got 120%, would you agree you should be worried? 98% is fine. 82% is not fine, right? So there's only a little wiggle room. And it's an easy check. If it's a really big table, it's a worthwhile check because WebAssign is so pernickety, it'll make you pull your hair out. Can you imagine a table where there's at least 50 different numbers, different things that you filled in the gaps? If just one of those, just one, is wrong, all it will tell you is the whole question's wrong. And so you'll get driven crazy because you're going to be saying, but I'm doing it right. And maybe the only thing you did wrong is that should have been, you rounded that off. Instead of 0.18, it should have been 0.17, right? That's all you did that was wrong. You just got to be careful. There's just no shortcuts. So there's one last guy. Who on earth is left? Well, he's called the cumulative frequency. Well, let's see how that works. In the first group, there is 6 people. Check. In the next group, there's another 14. The cumulative frequency is what you get when you add those 2 together. In the next group, there's another 5. So that makes the cumulative frequency 25. In the last group, there's 3. That makes the cumulative frequency 28. Does that kind of make sense? Right.
Yes.
Now, when you do a cumulative frequency, you can create a diagram of that. It's got a rather long-winded name. It's called a well, depends on the textbook, cumulative frequency chart. And let's show you how it works. Along the bottom, you put the test score. And we use the midpoint. So can you imagine I have 5.5, and I'm trying to do this equally spaced because it should be 15.5, 25.5, and finally 35.5. Looks like I need to get as high as, what, 28 here. So 5, 10, 15, 20, 25, 30. So I'm losing that scale. The midpoint 5.5, plot a 6. Well, kind of there. You agree? Roughly. At 15.5, do 20, which is here. At 25.5, which is the third number, go to 25, which is here. And at 35.5, the last number, go to 28, and it's about here. And then you basically try your best to join them up. And that's what a cumulative frequency chart looks like. It's also called an ogive chart, O-G-I-V-E chart, if you want to know another name for it. Now, if you're doing this guy correct, shouldn't the last number be 28? No wiggle room. It must be a nice whole number, and it must be the total amount of people that you got your data from. So this is kind of the whole kit and caboodle in one big meal. Probably a lot to digest, but hopefully you're getting the gist of this. I'm going to go right now and look at, oh, I've got it over here, good, and get an example of the kinds of things that are going to happen in your homework. Let's kick that off. Let's kick that off. Okay, I should be ready. Do you know if at first you don't succeed, then you shouldn't take up skydiving? Oh, I got somebody's funny bone at last. Christian, you seem to be a challenge. I'm going to work on you. You ready? Can you hear me? Okay, so let's see if I can find a joke that you might think funny. What do you do if you get attacked by a group of circus performers? You go for the juggler first. He likes it. Go look. Right. I just needed a little break there because I think we've absorbed enough. I want to give your brain a chance to put it into long-term memory. Has anybody got a joke before we actually look at the homework questions? The cornier, the better, by the way. I love corny jokes. Anybody got one? Has to be suitable, that's the only thing. Hey, what am I doing? Nothing? Okay, that's homework for next week. Okay, let's have a look at, this is one of the questions from your homework. It says a data set with whole numbers has a low value of 20 and a high value of 117, right? So the smallest number in it is 20. The biggest number is 117. And they want you to do a table with 7 classes, right? 7 groups, 7 bins, right? Different words, same thing. So I'm doing this bit that you can't see, but I'm verbalizing it. Don't you take the 117 and you divide it by 20, right? The biggest, take away the smallest. And in this case, they want 7. So I'm going to divide it by 7. And although you can't really see me, well, maybe you can see me do this part. I'm going to find out what we should use as our bin size. Oops, almost hit the wrong button there. To make it happen. And I am coming up with the number 13.857. Right, 13.857. There's nothing good about that number. So we'll just bite the bullet and say 14. Okay, so
Yeah, probably.
let's go for it. Smallest number is 20. If you're going to have 14 numbers in your group, do you end at 34 or end at 33?
33.
Right. Remember that little trick, you know, they do it. Now, if you set up the first one right, shouldn't you be able to do the others a lot quicker? Because isn't the pattern here 14, right? Everything's to do with 14. So I'm going to go down this group, and this one would be like 34. 14 more would get you 48. 14 more would 50. I hope if I don't screw up, I should get to the end in the right place. 76. 14 more is what? 80. 14 more is 94. And if I go to the other side, if you add 13 to that one, what went wrong there?
You added 4 instead of 14 for the
Which
column.
one? Oh, there we go.
7.
Thank you. I knew that I was wrong because it wasn't finishing with the right number, right? So do you see that adding 14 to 76 is 90, and then adding 14 to that is 104. Right, and let's just finish off the last one. Will the last one be 118 or 117? $118 or 117? What do you get?
117, right?
Right? Don't you add 14 and then remember to take one away, that horrible trick? Would you agree that this, I haven't filled it all in, but won't this table allow you to contain all the numbers from the smallest 20 all the way up to the biggest 117? Won't every single one of those numbers fit in one of those groups? So do you see that the process is working, isn't it? Big take away small, divided by how many groups there are, and you know, round up is always a good idea, and you're good to go. Very cool. Now you see this fellow here. These are examples of cumulative frequency tables, right? Diagrams, also called ogive curves. If you look at this one, here are the midpoints. Can you see them? And here they've done it not in terms of the frequencies, but they've done it in terms of the percentages. But that works just as well. So in which distribution then it says, does the most data fall below 20.5%? So let's see. At 25.5, about 35.7% of the data is there. In this one, it's what, 13.26, and in this one, it's 5. And we're being asked to pick from this 3 pictures, which one does most of the data. Between the 3 of them, which one's got the most? And that makes it that one. We go with that. So you're not creating these ones, you're just doing stuff with them.
Why isn't it the third one?
Did I screw up here? I thought I... Okay, let me... In which distribution does the most data fall below 20.5? And most data falls below, it's the first one. At 20.5, there's 35% of the data. Isn't that more, most, compared to the other two? That's what I'm getting at. Got to be careful with the English language. Right, this guy here, whoa. This guy here is basically everything that we did in class, right? We got a whole set of data, thankfully. Oh God, not thankfully, the buggers. I didn't swear. Right? That data is horrendous. I'm glad you're doing it and not me. Right, but that's what happens in real life. We are going to go through this data, at least to set up how to do all the bits that go here. I won't do all of it, but at least I'll give you a good start. We're going to figure out what the class width is, right? What the bin size is. Now, if we look at that data, and hopefully you can see it on your screen, I don't know if I can make this bigger. I don't think I can, unfortunately. As I scan through this data, I'm looking for the smallest number and the biggest number. Right now, my candidate for the smallest is 45. Can anybody see anything that's smaller than 45? Because I need to know that. Shall we go with that one? Right. I'm looking for the biggest. I can see, oh good. The biggest wasn't hard to find, isn't it? Because it's got 3 digits. So I'm looking at 101 in both cases. So would you agree that it's 101? Right. Now I'm going to leave that and go back into the white screen for a little bit, just to show you what I'm doing now. So you can't just hear me saying it, but you can actually see me doing it. We went through the data, we got the little guy, we got the big guy, and they want 6, right? 6 intervals, 6 bins. So 101 divided, take away 45, divided by 6. So I'm going over here, and I'm going to go 101, I'm going to take away 45, and then I'm going to divide that by 6, and I got 9.33 and a lot of 3s, right? So what I suggest here is 10. It's always a good idea to round up just to be safe. If you round down, you might end up with 7 intervals instead of 6. Right, so that's why I'm rounding up. Okay, now, our first group is going to be 45 to somebody, right? So this is me kind of going through the first row. Right, so let's get the headings right. There we are. $45 is the lower limit. Is the bigger limit 55 or 54?
54.
Are we getting comfortable with that little take away one thing? So that's guys done, right? That's lower and that's the upper. Now we're going to do the class boundary fellas, right? Aren't they basically 44.5 to 54.5? Now to get these guys, don't you just knock a 0.5 off this and add a 0.5 to that? Now I want the midpoint. Couldn't I just add these two and divide it by 2? Couldn't I add these two and divide them by 2? And you'll get the same midpoint. Don't know what it is yet, but I'm about to find out. 54, add 45, and then I divide it by 2, and I get a midpoint of 49.5. Are you comfortable about these 3 columns and where I got them? We good? Now, just for comparison's sake, shouldn't I be able to get the next one a lot easier? Because isn't the key number here 10? So,
wait, Professor?
Yes.
Wasn't the highest one 109? Because I saw 109 on the last row.
Oh, shooting space, did you?
Yeah.
Darn it. Oh, flip it up. I have great self-control. I did not swear at any of those times. Fix it. Okay. Can you pretend that the last few minutes did not happen? And I said to you, the smallest one was 45 and the biggest one was 109, right? So we will take 109, we'll subtract 45, and we'll divide by 6, and we'll see what kind of number we get this time. So 109, subtract 45, and I'm going to divide it by 6. And this time, I'm going to have to choose 11 because the answer was 10.66, right? So it's pretty much going to do the same thing again. I'm just going to do it with the correct numbers. Hopefully the smallest one was 45. Want to not add 11, but just add 10, right? So this one will go that way. Won't the boundaries be 44.5 to 55.5? That's good. Midpoint, let's see, 55, oh, interesting. A nice number for the midpoint.
The limit would be to 54.5, right?
This side?
Yeah,
the boundary is
55.5.
0.5 this side and then 0.5 the big side. So 45, this is 44.5, and on the other side, 55.5. So that is correct. That is the right boundary size. Midpoint is 50. Now we're right. Agreed? I'm now going to go back into our table and kind of show you what that would look like in your situation, because it is a really long question. So the class limit, 45 to 55. The class boundary was 44.5 all the way up to 55.5. The midpoint was 50. Okay, now we got some issues. Somebody better than me, because I'll screw up. Where's that 100 and thingy you saw? Oh, there it is. Look at the little bugger. Right in front of me. I should have seen it. Right. Scan through this data and tell me how many numbers are 45 up to and including 55. I'm going to do it in my head, and you're going to do it. And if my number's yours, we're using it. So I'm doing it a row at a time because that's just the way my brain works. So 45 up to and including 55. I was slightly disappointed. I have 2. Did anybody do better or worse than that?
I got 3 because there's another 45.
Tell me where there's one at the end of this row.
There's a
There's
46
one.
well in the second to last row.
Right, there's another one. Oh, there you go. See? Right, so will we go with 3 now? Anybody find another?
Where are you seeing this?
I can't hear you. Oh, you're not seeing it? Is that what you said? Oh, then we should make that happen, shouldn't we? Seen it now? Right. So after a lot of difficulty, you got 3. Me personally, if I didn't have to teach the class and because my scanning is so bad, I would print this out and then I could get a pen and cross them off as I see them. And that way I'm more likely to catch them and not count it twice or something. Right, now the total number of data points here should be pretty easy to calculate. 2, 4, 6, 8, 10, 10, 20, 30, 40, 50, 60, 70. So it looks like there's 70 numbers. Let's check. 3, 6, 7 rows. 2, 4, 6, 8, 10. So the relative frequency, won't that be 3 divided by 70? Right. So on my calculator, I'm doing 3 divided by 70, and I'm rounding this guy off. Did they mention anything about accuracy here? Oh, shooting space. They do. 4 decimal places. Okay, you want 4, you're getting 4. 0.042, and it rounds up to 9. And my cumulative frequency here is just 3. It's the number 3 because it doesn't say percentage cumulative frequency, right? It just says cumulative. Right, next group. Our interval size, our magic number was 11 now, wasn't it? Bin size was 11. So that makes this guy 56. And it makes this guy 66. And doesn't it make this guy 55.5? And it makes the other one 66.5. The midpoint is going to be 61. Oh, by the way, that was 11. We found that earlier. Okay, this is the last time we're going to do a frequency. I'm not even going to try because my success rate is 0 out of 0 right now. Somebody else scan through all that data and count how many times you see a 56 up to and including a 66. And if I get 2 people with the same answer, we're going for it. Whenever you think you're ready, just call it a number and I'll start listening.
I'm not sure I'm entirely correct, but I believe it's 7.
Right, we've got a candidate for 7. Do we get
I
anything
also
close?
got 7.
Right, that's, I ain't arguing now. We're getting it. We'll call it 7, right? Whoops, we'll call it 7. Right, now won't the relative frequency be 7 divided by 70, which is actually very easy to do? And won't the cumulative frequency be 10?
Yes.
Now, can you imagine that we fought our way through the rest of these and we got it all done? That would be this part B finished. Only one mistake. Can you just pretend that I can't count and that I make mistakes and I thought that was a 2? Right, could happen. When you go to the bit where you say, check my answer, do you know it's just going to say, you're wrong. So we need checks so that we can check ourselves before they tell us it's wrong, because you only get 3 shots and you don't want to use one of your shots up on something you could fix easily. Suppose that was 2 instead of 3, right? Vice versa, right? Suppose that was 3 instead of 2. How would I be able to check by just using the frequency column that I'd somehow made a mistake? Well, let's do it another way. What would the frequency column add up to if I did it right?
70?
Yeah. So if I had 2 and that was all I did, right, I scanned by one and I missed it, right? Wouldn't it add up to 69? And so I'd say, okay, I ain't moving on right now. I am not hitting submit answer button. I'm going to go hunting for what blinking guy I missed, right? And then hopefully I'd say, oh, darn it, I went and missed that guy in row 3 or wherever it was, and I'd fix it. What should the cumulative, what should the relative, well, rephrase it. What should the last number in the cumulative frequency be if you did it right?
70?
70, yeah.
Right? So if that last number adds up to 69, isn't that a sign you better go looking for something? Right? Something's not right.
Yes.
What should the relative frequency add up? Bearing in mind you're allowed a little bit of wiggle room because of rounding off. But roughly, what should the relative frequency look like if you rounded, if you added it up?
1.00.
Right. Darn close to 1 or 0.9998, that kind of number. If you get that, I'd be pretty comfortable. right? Phew. Now, since I don't have the whole picture here, can you see that there are 4 histograms, and one of these 4 histograms will be the right one for this data, won't it? So once you know all these numbers, you should be able to do it. Actually, I should be able to kick out 2 of them already. Won't I kick out this one and this one? Because frequency should be nice whole numbers, not decimals. Agreed? And when I look at that 3 and that 7 looks good. So I guess the only thing I need to worry about is which one of these 2 boundaries would you really be using when you draw a histogram? Would you use these numbers or do you use these numbers? That's your 2 choices. These or these. We only did it once, I know, but we did it in class.
The ones with
use the boundaries.
Yes, exactly. We use the boundaries. So even although I've not drawn that picture, can't I just by a process of elimination say it has to be that one? Because I know the frequency needs to be whole numbers, which means it can only be the first one or the 4th one. And then I know that you have to use class boundaries, so I got away with that one. It's kind of lucky. And now if it's a relative frequency one, right, as you can see here, they have relative frequency ones going on. Should relative frequency be using decimals or whole numbers?
decimals.
Decimals. So doesn't that mean I'll kill these 2 because they don't work? And I have 2 choices here. And I'm going to bet it's that one. And why am I betting it's that one? Because it's using boundaries. See that? Little sneaky. Oh, we could talk about this. We're almost finished. Categorize the basic distribution shape. It doesn't really matter if you use the frequency or you use the relative frequency. The shapes are still the same. So let's look at the shape of this. Is this shape here skewed right, skewed left, bimodal, uniform, or mound shaped? That's a word I haven't used. Mound shaped. Well, let's kick out the ones that it's not. It's not skewed right. Would you agree? It doesn't have a really skewed shape to it.
Does not
And it's
appear to
not
be.
skewed left. If it was bimodal, how many hills would it have?
2.
So it ain't that. I don't think I've mentioned uniform, but you know what uniform means, doesn't it mean they're all the same height? They're all the same. So it ain't that. So they've got a new guy in town called mound shape. Do you know I would call that unimodal? But I guess mound shape works. Doesn't it look like one hill? Mound shaped. Yeah, different textbooks have different labels. And we made it perfect timing. I asked for a joke at the end or halfway, whatever, and I never got any. Have any of you had a time to pick one before we leave? Because we need to have a nice joke to finish the week off. Teresa, you look like you're fun. Have you got a joke? Nothing. Ray? Ethan, you must have a joke.
Yeah, maybe.
Okay, go for it.
Okay, don't hate me for this. What do you call a guy with no arms and no legs tied behind a boat?
Oh God, no. Okay, go for it. What do you call him?
Skipper.
Okay, we're going that way. Right. To get this joke, you have to, and it's a very old movie, but if you've got little nieces and nephews, you probably had to watch it with them. And do you remember a Disney movie called Bambi? It's about a little deer. Okay, so here goes. What do you call a blind Bambi?
What?
No idea. What do you call a Bambi with a blind Bambi with 4 broken legs?
Thad?
No, still no idea.
No.
Yeah, well, he started. It was Ethan's thought. So this
Look,
one
he
is
forced
nothing.
it out of me.
Right, this one is nothing to do with Bambi. But where would you find a dog with no legs? Don't know. Exactly where you left it.
Oh man.
Pretty bad. Okay, make sure that you do your homework. You know that for the first 2 weeks of chapter 1 and 2, that is deliberately light because starting of the quarter, everything's going on and you're still trying to get your feet. Get working on the chapter 1 as much as you can. Get that all done. Try and get as much chapter 2 as you can. That way next week will be a bit lighter on you. If you wait until next week, 2 weeks homework in 1 week never ends well. So off you go. I won't look at my email much because, believe it or not, I do have a life and a wife and fun things to do. And I love teaching, but I also love other things. So if you shoot me an email, it might take me a day, but I will eventually get back to you if you get stuck on a homework question. Okay, bye-bye, guys. Have a great weekend. And I shall see you on Monday.
Bye.
Bye. Thank
Bye.
you.
You are
Bye.
welcome.
See
Have a
you.
good
Bye.
weekend.
Have a great
Bye.
time.
Bye.
Bye-bye.
You like my jokes?
Yeah.
Good. You got a good sense of humor, Courtney.
I'm kind of sarcastic. I don't have a lot of jokes.
Well, there's a little job for you. Part of your homework, get a really corny joke for next week for everyone.
I can do that.
Okay, I'll see you then. Bye-bye.
Bye-bye.